Hello, this is Mr. McLean, and I'm going to take you through the second part of our Chapter 5 review, which is part of the first unit exam for AP Bio. So we had spoken in the first section of the review of the material that covered up through Chapter 4, and I wanted to make this separate review just covering the content of Chapter 5 because it's such a important chapter as we kind of build our information that we need for the rest of the course. So if you look at the outline that I gave you of the highlights for what we need to know for the test, these are each of the units for chapter 5, and we start off talking about how polymers are built and how they're going to break down. So we want to do a quick review of that, look at a couple of images. Section 2 talked about the category of carbohydrates, where we went through and looked at the different categories in regards to mono and building them into disaccharides and eventually polysaccharides, and special emphasis on the type of glycosidic linkages. Section 3 gets us into the lipids, where we get a chance to look at some of the different characteristics of members of the lipid grouping. Section 4 is a very important section. We spend some time taking a look at the building blocks of proteins. We talk about the different types of structure that exists within a protein from the standpoint that there are 4 levels of structure. So we'll focus and emphasize that. And then the last part is actually a very brief intro to the nucleic acids. We spend a lot of time in genetics, so I'm going to kind of do a very preliminary introduction on that, and then we will move on. All right, so as we get into the material of Chapter 5, we were focusing on some of the general characteristics of being able to build polymers from the monomers. So the first slide that's really important for us is reviewing the 2 different key processes. And in this, we have the dehydration reactions, and we have the hydrolysis reactions. So when we look at how a dehydration works versus a hydrolysis reaction, I was drawing on here a few minutes ago. You can take a look anytime you have a small molecule or a monomer in this case, or in this case right here, we're actually seeing a small polymer, and we want to combine that with another unlinked monomer. Key things that we're going to see is that the hydrogen and the alcohol group are going to combine and they're going to form water. So anytime you have a removal of a water, you have what's considered a dehydration reaction, and the dehydration reaction is going to allow us to build a more complex molecule. So the end result is a longer and more significant polymer. If you do the opposite, you're talking about a hydrolysis. And anytime you have a hydrolysis, you are using water to lyse the molecule. So you're going to break it right here. So the addition of that H2O, here's the hydrogen, here's the alcohol group, and now you're back into 2 individual monomers. So any of those scenarios that we would want to come across, whether you're talking about the carbohydrates or if you're talking about the proteins or the lipids, they're going to follow that type of configuration. So first group that we have are the carbs, and these are, like I said, in many ways going to be our energy molecules, and we take a look at them. Their general ratio is going to be a carbon for every 2 hydrogens for every 1 oxygen. And if we look through the slides, one of the things that we're going to notice is that there is some diversity even with that same ratio. So you can have molecules that have 3 carbons in the chain. You can go up and see 5 or more. The most common ones are the hexoses, and in our case we're taking a look at glucose and fructose quite often. Now the picture right here is showing us a chain form, but when we go in here, most of the time our linear forms are going to be translated into a ring form because they're going to be in aqueous environments. And as a review, this picture right here is showing us the glucose in our ring form. And we can see all the carbons labeled on this one here. When we look at it most of the time, this is what we're going to see. And when we examine that type of setup, what you're going to notice is that it's not going to have the carbons labeled in each of these things. In fact, only in this example do they have the numbers. So the numbers are indicating the position, and when we ultimately start to put things together, that becomes critical. You want to make sure you understand this word right here, glycosidic bond or glycosidic linkage. And the glycosidic linkage is a specific type of covalent bond that helps us join different sugars. So in this case, if we're making a disaccharide, we use a glycosidic bond to hold those things together. So here's an example of making a disaccharide known as maltose. We're going to take our monosaccharide and we're going to take another monosaccharide, and once again, here's our continuous dehydration reaction, and what we're getting is we're getting an oxygen bridge. That's what this is referred to as, the oxygen bridge, and you can see that it's removed the water already. The other thing that I want to point out and review is this particular glycosidic linkage is named based on the carbons that are involved. So right here, you have it in the first position and it's bonded to the fourth position, so we classified it as a 1,4 glycosidic linkage. In the second picture, we have a different positioning that's taking place. So we have the first position on the glucose molecule matched up with the second position on fructose. That gives us a different kind of linkage. So just kind of keep that in mind. That becomes more important later on. We talked about polysaccharides. Just make sure you know that these are the big molecules. Some of the examples of the polysaccharides would be our starch molecules. Starch is a storage for plants. Here we see two examples, the branched amylopectin versus the non-branched amylose. The picture on the bottom is showing us glycogen. Glycogen is a storage molecule for how most of our animals get our glucose and store it in a reserve. And we store it primarily in our liver. The other categories of polysaccharides focus more on structural. So the number one most common polysaccharide and one of the most common organic molecules on the planet is cellulose. And cellulose has a lot of similarities to starch in the sense that you're going to have these large polymers of glucose, but the big difference is in the glycosidic bonds. And that exists because we have two different isomers of glucose. We have alpha glucose and we have the beta glucose. So if we slide up here, hopefully I can do that. For some reason I'm not. Moving some things around. All right. So if we slide up here and we do a quick comparison of alpha glucose versus beta glucose, we remember that the key difference is found right here and right here. So the fact that both of those have essentially the same configuration with the exception of the first position in terms of where the alcohol group is at, that creates the two isomers. Why that's important is whenever you take a look at something like starch, starch is going to have all of these alpha glucoses in there. And if you look at the position, it makes a 1,4, and each of these are a 1,4. But you'll notice that the oxygen bridges are all in a down configuration. Or if we flipped it, they'd all be going up. The point is they're all in the same direction. Now, if you look over here on the second half of this slide, and we go over here and we look at the cellulose, what we're noticing about cellulose is because it has this opposite type of isomer, it's creating linkages that have to flip the orientation of the glucose. So all the glucoses over in starch are all oriented with the same configuration. If you look here on the right side, the cellulose, it's kind of up and then it's flipped upside down. So the orientation gives us kind of this, and then the next one is kind of this. So what that does is it creates a different kind of structural characteristic. And basically, most animals do not have the capability of breaking down cellulose. So we can't digest that. We can digest the starch, but because of the non-digestible characteristics, that serves as dietary fiber. So when we think about the benefits of dietary fiber that cellulose gives us, basically we're unable to metabolize and break that down. So that would be one of the things that we're seeing, the insoluble fiber concept. The other final type of polysaccharide is chitin, and basically that is a polysaccharide that is found in exoskeletons, and we even made a mention about some of the biomedical application of that for different surgical threads. So section 3 gets us into the lipids, and basically the characteristic that you want to know about the lipids is that they are not going to have an affinity for water. They're going to be mostly hydrophobic. And the reason why they're mostly hydrophobic is a lot of these nonpolar covalent bonds. So these are the main ones. You got your fats, your phospholipids, and you have your steroids. So the fats, they fall into a group known as the triglycerides. And if we look at it, it has a glycerol and it has 3 fatty acid chains. So here's our picture. And this is solid fat right here. So the thing that you want to look for anytime you see an image like this is look inside the carbon chain of the fatty acid. And when you're looking here, if you notice that everything is full, there's no missing hydrogens, and therefore they're all single bonds. Anytime you look throughout here, these chains are going to be very linear. And as a result, they pack together very tight. So you can imagine over and over and over and over and over, it starts to form a solid, and it has the potential to obviously have negative impacts on our cardiovascular health. This over here, this component is the glycerol. And you can see, once again, we have a dehydration reaction. So this specific type of bond connection right here that deals with the lipids is what we call an ester linkage. So much like glycosidic was specific to the carbs, we have something that's going to be specific to the layout that we're seeing here with the lipids. So that's one of the major things that we would look for. Absolutely would be expected to be able to recognize that. So within the grouping of triglyceride, you basically have 2 main categories. Things that are saturated. The key with saturated is like that last picture, you didn't see any double bonds. All the hydrogens are there. You also can have the things that have unsaturated, which means that you're going to have a couple double bonds in there. And if we look at what that does to the structure, the big thing you're going to notice, if we compare a solid fat with a liquid oil, you're noticing right here that we have examples of double bonds. And the impact that double bonds have is bending of the molecule. And that's primarily going to be when you have the cis configuration. So as you're going through and you're looking at your carbon chain, and in your carbon chain you have hydrogens, kind of getting out of my ability to draw here, but I got hydrogens, hydrogens, hydrogens. I should have hydrogens all the way. We keep going, hydrogens. And if I'm missing a few hydrogens here, and I'm missing some other hydrogens, as long as they're missing all on the same side, and we form these double bonds, and if I have another section where, you know, I'm missing another set of hydrogens right down here, if they're on the same side, that is cis. If they're on opposite sides, so if I was missing up here instead of down here, that would be trans. Make sure you understand that. The process of hydrogenation, if we want to take something and go from being a liquid as an oil, and we want to bump that up and make that into a solid, we use hydrogenation to do that. Keep in mind, lipids are going to be a much more significant energy source, and on a gram per gram basis, you're going to get significantly more energy than you would from a comparable carbohydrate mass. Phospholipids are obviously pretty important when we think about the structure of our membrane. They're going to be a phospholipid made up of, or it's a 2 fatty acid chains with a phosphate group, and they're attached to the glycerol. And this is an amphiotic molecule, which means that when we look at it, this portion up here is going to be hydrophilic, So it's going to have polar characteristics, and this end down here is going to be nonpolar. All right, thank you.